a soil survey in the Zambezi River basin. So you'll find out if technically this is possible.
Hello, everyone. Can you hear me?
PhD Brecht Bamps, give us a moment. They are switching in the auditorium, so you are visiting right now online, but give us a moment, please.
Great, yeah.
We're already in the auditorium.
Okay, you are now be seen in the auditorium.
Okay, thank you. Good morning, everyone there. I am Brecht Bamps, speaking here from Belgium. And as introduced already, I will be giving a small talk on our insights from a soil survey that we did in Zambia a while back, and how we integrated the concept of soil catenas in our digital soil mapping approach, together with co-authors here mentioned on this slide. But first of all, some context into our research. I think I do not need to convince anyone here today of the importance of soil in itself, and also of soil class information and the availability of those soil class information. Because what we see still today is that certain areas across the globe still lack accurate and up-to-date soil class information at sufficient spatial resolution. What we see is that in those areas, often we have to rely on global soil products like soil grids at 250-meter resolution. That is excellent for global applications, but for some regional or local applications, more detailed information often is needed. And that was also the case for the Daphne project, which is actually the project within which our research fitted then for the soil part, where actually a decision analytic framework was made to deal with the water, energy, food nexus in the Zambezi River Basin. But of course, soil plays an important role here. So that's what we wanted to look at. And our objectives were actually more twofold. First of all, we wanted to actually figure out whether we could make classifications of the soils in the study area based on a limited number of in-field observations and limited number of laboratory analysis. And on the other hand, we wanted to evaluate multinomial logistic regression as a technique to come up with a soil class map, basically, of the study area. Now, so the location of the study area is within Zambia, which is largely covered by the Zambezi River Basin, as you can see here. So we worked in the gray area on the right map, the Opomolongoshi River Basin, covering an area of about 2,400 square kilometers. And we selected that area because there was a fast expansion of the larger and small scale irrigation taking place in this area. And also good to know is that for this sampling campaign, we had about 4 weeks time. So this is quite a large area to cover in that time period. Now, another important characteristic of the study area was a typical geomorphology, as you can see here, with this dendritic network of dambos, as they are called, which are these low-lying areas that get flooded during part of the year, or some areas even remain moist during the entire year. And throughout the study area, this dambo catena actually reoccurred everywhere. So what you can see here on this slide is the basic process you go through when you do a digital soil mapping exercise with, at the top, of course, crucially important, the ground reference data of the soils. So the soil classification based on field observations and laboratory data. And then on the other hand, another important input are the covariate data, the environmental covariates representing the soil forming factors. They are fed into the model. In our case, we actually made 10 different models with different sets of covariates, which were then later combined into one ensemble soil class map, which we will later discuss further. But first and foremost, essentially is the field campaign and for gathering the soil class data on the terrain. Initially, we designed a conditioned Latin hypercube sampling design, a statistical sampling design to cover the study area. But we soon noticed when we went into the terrain that this was really difficult to really stick to the sampling design, mainly due to accessibility issues, so that we couldn't reach a sampling point within reasonable time, or that we didn't have permission from the landowner, for example. So there we had to think on how can we adapt now this statistical design as to fit our practical constraints within where time also played a very important role. So there we shifted more to this catena concept of the sampling design, trying to cover these dambo catenas throughout the study area with various spatial extents to cover the variability as good as possible. And this then resulted in 90 locations where we were able to dig profiles and collect samples. And then, of course, we had to make our classification with the profile observations and the laboratory analysis. Also here, we had some constraints on the budget to derive the physicochemical properties of these different on these different profile locations, as well as the sampling that we took was not based on the horizons, but on fixed depths, so at 30, 60, and 90 centimeters, bringing some complexity into the classification. But of course, we still had our field observations to rely on to then do the classification according to the WRB 2015 version. So I mentioned the other important set of input data, which are the environmental covariates. I will not go into detail, but basically they represent the most important soil forming factors. And here, when you select these covariates, it's important to have a rigorous methodology of doing so, because including or excluding a particular covariate will have a substantial influence on your final result of your soil map. Here, the formula apparently disappeared, but it was the formula for the multinomial logistic regression model that we trained. And we opted for this model because it allows you, on the one hand, to work with relatively small data sets, and it is not a complete black box, which occurs with some other methodologies. So here you could really have an indication of the direction and magnitude of influence that a certain covariate had on the probability of occurrence of a certain soil group. So what this algorithm does is it gives for every soil class or class that you want to model a probability of occurrence for every location. In our case, we worked on the reference soil group level, so we got an estimate for every reference soil group level, the probability of occurrence thereof. And also good to know is that we worked at a spatial resolution of 30 meters. So I mentioned that this technique allows you to work with a limited data set, but there are also limits to that use, of course, because not every reference soil group had the same amount of observations, causing sometimes some numerical inconsistencies in the model. And that's why we opted to create 10 separate base models with different sets of covariates, and then later combine them in an ensemble soil map by equal weights averaging, which allows you to deal with some of those issues. And then finally, of course, comes the accuracy assessment. Now, when we look at the results, we can see here our 90 observations throughout the study area. You see a lot of acrisols and lixisols, and also that gleysols and plintosols occurred frequently in the data set, but then also you can see the large variability in number of observations per reference soil group. And here it's also good to note that, first of all, the model can, of course, only predict reference soil groups that you put into it. That's the first. And then secondly, it tends to predict the reference soil groups better that have more observations. And this is how that looks like in the field. So here we can see this typical catena that we would encounter with this Dumbo structure, basically. Where at the Dumbo bottom, so the area that was flooded during part of the year or submerged year-round, we would typically find gleysols and adjacent to it vertisols. And then when moving up the slope, we encountered a recurrent pattern of plintosols with this plintic, often pisoplintic and petroplintic materials, and often sometimes even huge petroplintic slabs coming near the surface or even being completely at the surface. And then when we move more upwards, of course, there is a gradual transition towards plintic acrisols and lixisols. And then at the interfluve areas, really on top, where most of the large-scale irrigation was practiced, we would see these acrisols and lixisols occurring associated with phaeozems. So this is actually a nice overview of the general pattern that we encountered throughout the study area, actually. And the same can be seen here from our model outputs. What you see here is what the multinomial logistic regression gives us as an output with a probability of occurrence estimate for every reference soil group. For example, when looking at the second map of the gleysols, again, that dendritic network of those Dumbo bottom areas is clearly recognizable in there. And in the next step then is to combine these probabilities and look at every pixel what the reference soil group is with the highest probability of occurrence, which was then selected for that location. And that then results in this map, which is the final product. This is our ensemble soil class map with the reference soil groups. Clearly, representing the spatial variability of the soils within our study area, and also concurring to the field observations that we did. But of course, it's important here to note that we did our modeling on the reference soil group level, but when looking at it from the classification standpoint, often the difference between a petroplintic acrisol and a real plintosol can be relatively small, whilst here they are modeled as the reference soil groups without the qualifiers. So it's also important to notify this that these qualifiers, especially when you're talking about, for example, petroplintic as a qualifier that can have vast impact on the land use and land management on a certain location. So that's a good thing to keep in mind, and also something that is maybe an idea to still do in the future is to not only look at the reference soil groups, but we could do the same exercise on the level of the diagnostic feature, for example, to make an estimate on the probability of occurrence of this plintic, petroplintic, or pisoplintic horizon in the soil, which might be very useful to know for the actual land users in those areas. When we then look at accuracy, here we see the result. In the middle is what we reached with our final product of the soil class map, the ensemble soil class map with a kappa coefficient of about 0.36, which is considered as in fair agreement with reality. Of course, this product is far from perfect, but as we compare it to information that was previously available, in this case represented by soil grids, we see that, of course, by adding our observations and our digital soil mapping technique, we were able to increase this substantially. Yeah? And on the other hand, also note that we were able to map 7 reference soil groups, while soil grids at the time only represented 2 reference soil groups occurring in our area, and hence missing a lot of valuable information. And here it's then also important to note that this concurs with the call for continued efforts for fieldwork and adding to our list of observations, because we can only model make our models as good as the data that we put into it, of course, but it's certainly true for soils as well. And these efforts are certainly needed to improve and complement extremely useful global soil products, such as soil grids, and to make them more suitable for smaller scale applications on the regional or local scale. And then here, to conclude, I want to give some take-home messages. So first of all, we were able to classify our soils given the limitations that we were working within. And also we were able to use this multinomial logistic regression with a limited number of observations. And then secondly, important was that given the difficulties on the terrain for the implementation of a statistical sampling design, we had to shift to this Dumbo catena approach, where that was used as a conceptual model for pedogenesis to come up with an optimal coverage of the variability within our area. And lastly, we also saw that our final ensemble soil class map performed better than the individual base models, and also performed better than the soil information that was present already at that time via soil grids. So yeah, thank you for listening, and I'm happy to answer questions.
Well, thank you for your nice presentation, and hope you will understand our. That's great.
Yes. Yes.
Okay, I have a very simple question in the beginning. You did all the things with different models, and but in the beginning, yes, the places where you sampled and the analytical procedure, this was in a very traditional way done. So in the future, will it be possible to start with modeling and with the models already decide where you should take samples and which analytical data you should produce?
Yes, indeed. That's an interesting remark, and that's actually what the original plan also was. So there are these statistical techniques to optimize your sampling design, such as this conditioned Latin hypercube sampling or a k-means clustering, where you already take into account the environmental covariates and their spatial variability to cover their variation as optimally as possible. But of course, then when you go into the field, that's a completely different story. And then often you need to rely on on the more classical approaches and these conceptual models of pedogenesis to adapt the sampling design to those conditions, which was at least the case for us, working on a relatively large area with a limited amount of time.
Thank you. And do we have other questions? We must use the microphone, otherwise not possible.
Thank you very much for this clear presentation. I have just one question. On the map, you showed us that you have mostly the soil units which are connected with the tropical regions, like the Lixi soils, Pinto soils, and others. But also, there was clearly visible that it was along the valley of the rivers. There was a lot of arenasols and regosols. How do you interpret them? Are they connected with the soil erosion, which is in this region, or in other way?
Yeah, indeed. So there, the regosol and arenosol, I clustered them in one group because we only had one arenosol observation, and then it would give difficulties in the model, but they were anyway closely similar to each other, the regosols and areноsols that we encountered. But they indeed also were seem to occur more on the slopey areas and seem to develop in colluvic material. If that answers your question.
We have more questions? Okay. Sergei Sedov.
Thank you very much. This is really very interesting approach and very interesting model for soil mapping. I think the key element here is the establishment of probabilities of certain soil classes. And my question is, I didn't understand quite well, how did you ascribe the relative weight of environmental variables for definition of position of certain soil group? What was more important, what was less important? I see that finally the map is mostly according to relief, but there are some other variables, yes?
Yes, so the most dominant factor indeed was those associated to relief. So we had multiple indicators thereof, elevation, relative elevation, slope, etc. And were really those that played the most important role. For example, the climatic variables didn't really have a substantial influence, we think, over the size of our study area. So this geomorphology seems to dominate it, but of course that is not the case for the plintosols for itself, because they tended to occur more in the south of the study area. But that's then more related to historical climatic conditions, which we did not really capture in our covariates, I think. But that's a difficult thing to do.
Thank you.
Thanks. So we have one more question. This will be the last one.
Yes, my question is not that scientific, because I wanted to know, maybe I missed that part, if local communities or local people have participated in your field work, and if the results from the laboratory are also local results or from Belgium.
Yeah, so the fieldwork was done by me and my then supervisor Mulenga Kalumba, who was originated from Zambia. And we also were assisted by 4 locals who helped us with the pits. And then the analysis we did in Belgium. So we flew the samples to Belgium. And there also were then limited in the amount of samples we could take, of course. And then the samples were analyzed at the laboratory at the university in Belgium.
Okay, so we have to close. Many thanks again for your excellent presentation and discussion. I would like to keep you in the auditory here, but this is not possible. But it was